Good day, everybody, and welcome to the IEEE SUSTECH webinar series on the technology for the circular economy. And the circular economy, as you know, the world of we have a finite resource, and then we have to basically move away from the traditional take and make and dispose model, and to the reduction, reuse, refurbishing, and the recycling mode. So this is the basically come from the United Nations Environmental Program. Next, please. So from the IEEE point of view, IEEE is a technology powerhouse. So we are going to ensuring that our response to the climate change is substantial, appropriate, and properly engaged. So that on the IEEE member and the technical profession. So IEEE provide a neutral platform and will function as a technology providers. Next, please. So for the SUSTECH, the webinar series, we try to intend the broader audience, not only the engineer technical communities, industry regulator, and then policymaker and community stakeholders. And for the general community, with an interest in climate change, sustainability, clean energy, and industry, the health of the planet, its resource, its ecosystem, and its inhabitant, and the related topics. We serving the need for the profession and the public by increasing awareness, understanding of the technologies. Next, please. So this webinar series, this is basically the list of this year's webinar series, the topics that we have covered. Though this is the last one of this year, the topic is talking about recycle and the reuse battery that Dr. Chamalala has expanded from the original EV to the grid storage and in the industry strategies. So it basically give you people a broader view on the battery storage system. And so Dr. Babu Chamalala, he just recently moved to the University of Texas at Arlington. Before that, he was served as a senior scientist at the Sandia National Lab. And he was head of energy storage technology and the system department and the program manager for grid energy storage at the laboratory. So before he joined the Sandia National Lab in 2015, he was a corporate fellow of MEMC, Electronic Material Sun Edition, where he led R&D and the product development on energy storage technologies. So he has a very broad background, and you can see he started from the electronic side and then moved to the energy storage and to the power systems. So that is the basic. He is a distinguished lecturer of the IEEE Power and Energy Society and the fellow of the IEEE AAS Material Research Society and the National Academy of Inventors. So in 2024, he was elected as the member of the National Academy of Engineers and received the IEEE USA Harry Diamond Memorial Award. He was the past chair of IPS Energy Storage and the Stationary Battery Technical Committee. He is currently served as a vice president of conference and the meeting of PES and the chair of the Grid Interface Committee of the IEEE Transportation Electrification Council. Let's welcome to Babu Chamalala.
Thank you, Wajin. It's a pleasure to be on this webinar series. Well, thank you for bringing me on board to present on recycle and reuse of batteries. I'm going to focus today's presentation on how the EV industry and the grid storage industry is looking at recycling and reuse as these two industries rapidly grow. This is kind of a quick outline of my presentation. I'm just going to give just an overview of the battery industry, where things are, and what are the technology trends, and what are the things that are happening in the broader scheme of things, and then talk about industry practices in lead acid batteries, which have been the lead technology for 100+ years, and they have recycling is well established, and then discuss about recycling and reuse strategy in lithium-ion batteries. That is, what are the technology which is driving EVs and to a large extent the grid storage industry. And there are other technologies, including flow batteries, that are also being considered for grid storage. And we'll quickly talk about what are the recycling challenges and how industry is proceeding with recycling and reuse on flow batteries and other technologies. And then what are the typical engineering challenges and how the industry is addressing. And we'll have questions and answers and some discussion at the end. So to quickly give a summary of what we have a range of battery technologies. I mean, if you look at batteries as an industry, you have the traditional batteries like lead acid, zinc, nickel batteries, nickel metal hydride batteries, and these have been in somewhat fairly mature technologies for many years, right? And those industries are fairly well established, and they have practices on recycle and reuse where it makes economic sense and where the regulatory practices are in place. And then lithium batteries is the new technology for the last 30-some years. Primarily started with consumer electronics, and now evolved into core technology for EVs and grid storage. Then you have high temperature batteries, things like sodium sulfur, sodium nickel chloride, which have been in production for almost 50 years. A lot of these things started at the same time as the first oil crisis. So that's where lithium, high temperature batteries, even flow batteries, they all got started as new industries. So then you have redox flow batteries, primarily vanadium-based systems that are in production and deployments. And then the range of emerging technologies, you hear about solid-state batteries, sodium-ion batteries, lithium-sulfur batteries, and a whole class of metal air batteries for longer duration storage, including iron air and zinc air. And these technologies serve different applications, and so they have their own unique markets. So, for example, if you look at the lead acid and zinc nickel batteries, they go into UPS systems for industrial applications. Now, large-scale data centers, you have UPS everywhere. And these are also typically the backup power for critical systems in buildings, industrial plants, or power plants, or anywhere else, or substations, right? Then lead acid has been the core technology for automotive start-stop applications, and also for things like forklifts, traction applications. And for consumer electronics, initially we had lithium metal hydride as being the early technology because it was available, and now everything has migrated completely lithium batteries. And the same is true for mobile devices, electric vehicles, and to a certain extent, grid storage. So those are the big applications for these technologies. So just to give you an idea of how big these technologies are, how big the scale is, and how much manufacturing capacity do you have, and where things are. So if you look at lead acid, which is the dominant technology for automotive start-stop and UPS, and that's roughly 80% of the market for those two applications. And globally, you have about 600 gigawatt hours of manufacturing capacity, and the US about 165 gigawatt hours. And this is a technology which is, recycling is very well established. And over the last 10+ years, there has been a lot of significant drive to build capacity with lithium-ion batteries, primarily for the EV market. And now we have roughly close to 4 terawatt hours of manufacturing capacity globally, and primarily serving the growing EV business. And most of this capacity, I would say, is primarily in China, Korea, and Japan. And now rapid capacity growth is happening in the US with the automotive majors setting up plants. And those are the two technologies where there is enough volumes to sustain recycling and reuse. Nickel zinc and flow are the other technologies that are in volume production. And I think they have enough volumes to support recycling. So coming to lead acid battery technology, I mean, this is very mature. I mean, lead acid batteries have been in use for almost 150 years. And it's a slow growth in the automotive industrial markets. UPS is rapidly growing for the data center applications. And recycling infrastructure is extremely well established globally. And you'll see it in the next slide on where the recycling is. Most of the large companies in the lead acid business have recycling, and they have end-to-end control. And many of them have in-house recycling enterprises and plants, right? Then there are pure play recyclers who either have joint ventures with large lead acid battery companies or with recyclers, right? Then there is in some countries, you have diversified conglomerates who are in the recycling business. So those are the three different supply chains. And at least in the developed markets, we don't really produce any more primary lead. I mean, the recycling is so efficient. We source most of the material needed for new lead acid batteries from recycling. So that tells you the story. Lead acid batteries are fully recycled, and there is a well-established supply chain to do the recycling. And just look at, as an example, how this happens in the US. So if you look at the US, recycling of all products, let's say aluminum cans, consumer electronics, plastic bottles, lithium-ion batteries, lead acid has close to 99% recycling. And it's higher than lithium, higher than plastic cans, right? And how that happens, why it's so efficient, I think, the industry has embraced recycling as a way to get way to be environmentally sustainable practices, and also lithium lead acid systems are recyclable by design. So this kind of data shows you, this is data coming from Battery Council International. Battery Council is a business group which supports lead acid battery industry. They did a 5-year survey on recycling practices in the US. So as you can see, if you look at the shipment of volumes of, close to 400 million units, pounds, and how much of the lead is recycled. It's almost like over a 5-year period between 2017 and 2021. Most of the lead that goes into the systems is more or less fully recycled. So the industry has done a good job in reusing batteries for reusing and recycling. And what made the lead acid battery industry so efficient in recycling, and what are the best practices? I think this is a lesson we have to take as we look at the lithium battery industry. First of all, I think the lead acid battery industry has embraced recycling as a business practice, and I think they also wanted to be stewards of environment, because lead poisoning is a critical issue, and there are policies and regulations in place to make sure that lead poisoning doesn't occur, and we don't have disposal of lead batteries in waste streams. So that is the most important thing. The other thing is design for manufacturability and recycling. From the day one, the systems the batteries are designed to be recycled. So you have a closed loop approach to manufacturing. Battery packs are designed with recycling in mind, so that the pack design itself is easy to recycle. And leads resmelting, plastic casings are fully recycled, and also for the most part, the acid is recycled into sulfates, which go into industrial applications. And many of the bigger companies have their own recycling plants or operate the recycling business with partners. So I'll show you one example of a large company which is doing recycling almost 100% by themselves. For example, here you see a graphic from East Penn Manufacturing. East Penn is the largest single-site lead-acid battery manufacturer in the world. And in this single site, they bring in all the batteries that they ever produce from their factories. So they have a capacity for about 30,000 batteries per day. And they recycle 200 million pounds of lead every year and about 11 million pounds of plastic. So everything that goes into a lead-acid battery is brought back and fully recycled in one site. And this is not a common practice with all the companies, but I would say this type of practice is globally embraced by the larger companies. And typically, you bring in all the batteries manufactured back to a single site, either through an aggregator or by OEMs. So this is well established and successful as a business. So now coming to lithium-ion battery industry is the leading technology for lots of things now, right? And this is an essential technology for mobile devices and all things portable. That includes now widespread applications in medical industrial markets. And unlike lead-acid batteries, where you have form factors which are well standardized, lithium-ion doesn't have the same level of standardization, and the form factors have a wide range, from small battery packs for consumer electronics to a bunch of other things, industrial applications, medical devices, and then larger devices, larger form factors for battery packs for EVs. I mean, typically you think of EV battery pack somewhere between 50 to 100 kilowatt hours in energy density, energy capacity. And then there is a variation in the type of material technology that you have in the battery. So for example, if you look at consumer electronics, they tend to have lithium cobalt oxide, much more energy dense and higher voltage. And they're also moving towards LFP, which is the cheaper and from a materials point of view, and also better safety profile. With electric vehicle batteries, primarily nickel manganese cobalt or nickel cobalt aluminum, those are the two big material systems that they use. And LFP is becoming more prevalent as it's cheaper in cost and also has a better safety profile. And the industry is getting the volumes to support reuse and recycling, and the businesses are getting established, okay? The grid storage is also a growing segment, but not as big as the EV industry. Unlike electric vehicle batteries, grid storage tend to have a lot more LFP because you don't really have high power requirements. You want higher energy capacity, but not necessarily high C rates, unlike in a car. And here, the battery pack technology is very different. You're building large battery packs in 19-inch racks, and they make them fairly modular and put them in large 20 and 40-foot containers. And typically, each container may have anywhere from 1 to 8 megawatt hours in storage capacity. So recycling has to think about how do you recycle a whole container. So what is driving the industry? I think the scale is there now. The manufacturing scale is large, and the capacities are growing pretty quickly. The energy density is increasing because you want to pack more energy in a small volume, both at the cell level and the pack level. So the cells and packs are becoming smaller, more dense. And how do you thermally manage these things is what a lot of the battery pack engineering looks like. And the battery packs for EVs are fairly large, as you will see. And consumer electronics, the form factors are very different, and the supply chains are also very different. And the models for recycling and reuse are quickly evolving depending on which part of the business you're looking at. So where is the capacity growth coming globally? Many, as you can see it, I mean, in most of the capacity growth is primarily happened in China over the last 5 to 10 years. And slowly that growth is coming to US and the rest of the world, primarily driven by the EV companies. And where did this capacity go is also important. If you look at the slide on the right side, you will see the projections for EV and battery storage deployments, and almost majority, maybe 80-90% of the capacity is going into the EV market. And that's what is going to drive the recycling business going forward. And the numbers, I think, as you look into 2040, 2020 time frame are significant enough, and the volumes coming out of retirement of batteries will be large enough. And coming to the US, we are looking at the rapid buildup of factories now, and you hear about a large number of gigafactories being built now, and the capacity is at some point, installed capacity is somewhere in the 700 to 800 gigawatt hours right now. That'll reach close to a terawatt hour per year. So that'll supply the volumes needed by the large EV companies and automotive majors, and some of the same capacity is going to the grid market. And most of these plants are large plants, and with capacity anywhere from 20 to 40 gigawatt hours per year. And a typical gigafactory has somewhere in 30 to 40 gigawatt hours production capacity. So what are the end-of-life material streams that can sustain a recycling business in the lithium industry? So that could be from consumer electronics, and there are companies who are involved in collecting electronic waste, and they recycle the batteries. And there are they're essentially these companies work with consumer electronic companies like Best Buy and Walmart's and everybody else where used batteries come in, and then they go into the recycling streams. EVs and the grid mobility sector, with the large volumes they have, they are a lot more strategic on how they do it. Okay, and also you need to think about large plants in production. Even a small amount of scrap, even if your production volumes at production volumes in the tens of gigawatt hours, even a small amount of waste will be significant. So the scrap from manufacturing is also significant as a recycling stream. So, but the industry is still fairly nascent. I think the regulatory frame in place in many places to collect all batteries that go into waste streams, especially in the consumer electronics space. And the business models are emerging, how to monetize, how to develop a viable business models to sustain an operation. So form factors, as I mentioned, very different, depending on which technology and application you look at. If you look at consumer electronics, your typical cell phone has a single cell battery, is a pouch cell, so it's a flat form factor. And if you look at laptops, they all move to pouch cells, single cell, primarily single cells, somewhere in the capacity in the 10 to maybe as much as 50 watt hours. Then commercial industrial, you may have a battery module anywhere from a kilowatt hour to maybe as big as a megawatt hour large module. EV batteries, their own class. They're designed as fully integrated, almost hermetically sealed systems because they have a significant amount of thermal management, because EV batteries have to do high C rates because you're going to ramp up power. It's essentially in the beginning is a power application, then move to energy application. So they have high C rates for short times. So the packages have to be designed with a lot of thermal management, mostly all and hermetically sealed thermal management. So the pack design is almost like each company had their own battery pack. So it's not standardized. Utility scale, as you can see on the bottom, these are 40-foot containers, and you have 19-inch racks, and they're all battery banks for each rack. So a typical battery in a grid storage system may look like what you see in the bottom image. That's anywhere from 1 to 8 megawatt hours, and 4 megawatt is pretty common, and 8 is becoming more common as the energy density increases. So from a recycling point of view, you got to think about form factors and how do you actually disassemble and reuse all the different material streams that come out of different packs. And as an industry, if you look at it, you have primary raw materials, starting with the mining, processing, and midstream, cell and component manufacturing, and the pack manufacturing, then we come to the end of life, okay? And that's where you got the volumes to sustain recycling and reuse. Unlike lead-acid batteries, lithium-ion batteries is fairly complex. It doesn't have one material that is going to be really valuable to easily recycle. That's part of the primary challenge. And as you can see in the graphic, if you look at what are the core materials that are going to be really important to recycle, it's lithium, cobalt, nickel, and those are the three materials you have. And 22% graphite. I mean, that's usually not recycled because it's very difficult to separate graphite. And then you have aluminum and copper electrodes on both sides. Then you have a can, which is typically a metal can, which is the packaging. So, and electrolyte is not recycled. So there is only a small volume of the material that can be essentially recycled, okay? And that is the material which has commercial value and also makes sense. So I think, this complexity of the cells and modules in lithium batteries make the recycling not as simple as lead-acid batteries. So what is the difference between lead-acid batteries and lithium batteries from a recycling point of view, right? I mean, lead-acid batteries, you have one technology, one material system, lead frames, lead paste, and plastic casing, and an electrolyte, right? So all of them are designed to be recycled. 100% lead is recycled in that sense, right? And the regulations in place. So the system is designed and have the inherent materials technology that supports easy recycling. Whereas lead-acid, lithium-ion batteries are complex systems. You take the cells, you put a BMS on the top of that, then you put a pack, and then you integrate that with packaging and thermal management to make it a module, right? And so it's fairly complex. So to recycle, it's a somewhat significantly manual process. I think companies are trying to evolve what is the best way to recycle and reuse. So, and I'll show you one example of a company which is doing it. Before we go that, people talk about second life. Okay, EV batteries, I think they retain good amount of capacity. Most EV batteries, automotive companies decide they reaches the end of life around 80% of the initial capacity. As you can see, depending on the technology, you may have significant amount of life still available, even if you reach 80% of the capacity, right? So the graphic shows the charge characteristics of three different chemistries, LFP on the top, which is in the blue, and LFP has significant life even after 3,000 cycles, right? NMC and NCA, which are more power devices and they are widely used in cars, they have less amount of life available. But most car companies think of 1,000 cycles as the end of life, and that gives you somewhere in the 80,000 miles of warranty. So there is a significant amount of life. Knowing which batteries have the life and how do you qualify is one of the key. So there are business models companies are evolving on reusing these batteries cost effectively for some applications. That's the key. But there are common challenges on reuse. We don't know the state of the health of the batteries. They vary from cell to cell, sometimes from module to module. And cells degrade variably in many cases. Then you need to look at the cell balancing issues, and that leads to pack level stability. So how do you ensure that your performance is stable from a battery pack? And most of the time, all these battery packs are packaged with a proprietary BMS. There's a battery management system, which is essentially needed for lithium-ion batteries, which is not the case with lead-acid batteries. They don't have a BMS. And many manufacturers don't share their life cycle data. So for reuse, unless it's proprietary, you would not know what is the historical behavior of the battery pack is. So that is a challenge. And age cells and battery packs, they have safety risks. I mean, you hear about significant fires in warehouses where used batteries are stored. So safety risk is real. So how do you reduce the safety risk of battery packs before they go to recycling? And then standardization, packaging, BMS, all those things would really help. Okay. That's where I think the big things needs to happen. The other thing is, if you are going to go after an application which requires a warranty or some level of comfort for end user, then you want to have performance and warranty issues. How do you provide a warranty for a reuse application is also another challenge. And then the whole economic aspect of, does it provide a profitable business for a company to develop a recycling business or reuse business is still, I think, lots of pieces coming together. And the regulatory framework and compliance are not really in place, unlike in lead-acid batteries. So with that, competition is growing in reusing lithium-ion batteries for specific applications. I think there are companies building battery banks for grid storage applications using used batteries and stationary storage. And what we need is, the BMS and control systems needs to become more open. That will help. And reliability issues, I think, we need to have some level of a predictive way of knowing the second life. How much capacity do you have in your second life battery? It is difficult at this point, but I think, that's what needs to happen. Then how do you overcome some of these challenges? I think, the industry is moving in the direction, but there are still issues. I mean, we need to have better diagnostics and sorting. A lot of these battery packs come to a warehouse, and we want to know what the state of the health is and what the remaining life is. And equipment needs to be designed that can test in an automated fashion to give you a good sense of the state of the health and the remaining capacity. And the industry, at least at some point, need to look at the adaptive BMS so that you can take a range of technologies and still be able to do the recycling part really quickly. And then pack design can be more optimized for recycling. Right now, pack design, at least in the EV space, is designed for form factor that go into a car, and the car performance is what determines the form factors and the pack design. So, and thermal management and the regulatory stuff, those are all coming. So I want to give one example of a company which has taken this to a significant level. Redwood Materials, based in Carson City and Lake Tahoe, has built a sizable operation to recycle lithium-ion batteries. This came out of some of the people from Tesla. So they have built a large-scale facility where they go from recycling to reuse in one place, right? And they have 80,000 megawatts, 80,000 metric tons of capacity to process a year. And they get most of the scrap from the EV automotive majors. And roughly the capacity is about 500,000 cars per year. That's equivalent to 40 gigawatt hours of capacity. And where do they get the capacity? As I'll show you in the next slide, it's mostly from all the auto OEMs. But they built on a single site. You take the used batteries, they sort them for reuse, and some of them will go to reuse for grid storage applications. And those which are not good enough for reuse, they go into the recycling, where they can get the materials out, lithium, cathode materials, cobalt, nickel, all those things. They come out as raw materials that can go back into primary production. So they have developed a full-scale supply chain with major OEMs. I mean, Toyota, Volkswagen, Tesla, and everybody else, right? They're also working with the cell manufacturers in the US, Panasonic, which supplies cells to Tesla and Toyota, and Ultium, which is the GM joint venture with LG, and the LG Energy Solutions. Those are the primary cell manufacturers. So they have a supply chain in place to secure raw materials for used batteries. So, and that's the business model they have. And this is one example of reuse of batteries for energy storage. So once they qualify cells to be of use and have good life, they start packing them, still using the existing packaging from a EV platform, and qualifying them and building them as storage units for grid applications. On the right side, you see a large grid storage plant that they built for a data center, Crusoe. This is about 63 megawatt hours of storage that came from used EV batteries, and that supports 12 megawatt AC power for the data center operation. So they have shown that there is a model for reuse for grid storage applications, but that's because they have a full cycle from use to reuse. That's a model I think made it successful. So what does Redwood Materials think of the future? I mean, as I look at the 2040, 2050, the volumes for recycling will be in the 500 gigawatt hours per year type numbers, because if you were to believe in EV transition happen in the next 20-30 years fully, then you will have the volumes to support recycling on a larger scale. Then coming to flow batteries, I think these are technologies well suited for grid applications where you can separate energy and power, and that has been the interesting aspect of this technology. And this technology is being deployed in large plants, but not at the same scale as lithium-ion based grid storage systems. But these are still in a fairly small volumes. So, for example, Runkey Power in Dalian, China, they have built a 400 megawatt 4-hour battery, which is 400 megawatt hours vanadium flow battery. In this case, vanadium in an aqueous electrolyte, sulfuric acid electrolyte, is the primary material. These are significantly low energy dense, significant amount of water and acid in it, but the material can be fully recycled. For example, the electrolyte can be recycled, and the primary metal is recycled. So the business model is evolving on recycling vanadium flow batteries. So these are some of the critical gaps that we have in addressing recycling and reuse. I think lead-acid battery industry provides a good example on what makes a profitable recycling business model, right? And how do you port that to the lithium business is what is happening now, and that business is evolving quickly. So some of the challenges, I think, we have the recycling infrastructure is still not really well established. I think it's growing, but it's not fully there. Again, policies, regulatory framework would help, and that's lacking in many places. And the other important thing is, standardization battery pack formats in the EVs will really help to push recycling and reuse. And the business models have to become robust and profitable to become viable. With that, I will stop here.
Well, thank you very much, Dr. Chamalala, and for this comprehensive webinar presentation. So if you have any question, please put into the Q&A. So on that way that Babu can provide an answer for you. Well,
can I go out of the share mode and just be on Q&A?
Yes.
Okay, thank you.
Okay, so that do we have one question?
Yep.
Say, okay, from Charlie, that is, are EV batteries more robust to having unpraimed file if they are reused for energy storage, are they better?
The answer I would say is they're better because they're designed with the thermal management as part of the package, right? They're very highly engineered to provide a robust thermal management. So typically liquid cooling of some sort. So in that sense, EV batteries are much more safer than a typical battery pack. A typical battery pack in a normal grid storage system, the thermal management comes in the rack, not necessarily at the pack level.
Okay. Any other question from the audience? Well, that before we are while we are waiting for the input from the question from the audience, I have one question. One is basically you talk about high C, low C. What is the basic definition? I know most of the people in the battery industry understand the term, but for the general public, can you explain that
Sure.
the definition of the C?
So C rate is basically, let's say if you have a kilowatt hour battery and 1 C is discharging 1 kilowatt hour in 1 hour, right? So you are discharging the full capacity of the battery in an hour is 1 C. In EV batteries, you need to have many more C rates because in the car, for example, automotive in a car, starting is very power intensive. So you need to have high power capacity. So you operate them many more C, 4C, 5C rates. And the energy applications tend to be a 1C or a half C. Let's say, for example, if you have a 4-hour battery and you want to discharge over 4 hours, it's C over 4. Or if you want to have a battery that will last for 12 hours, then it's C over 10 or C over 12. And those are the types that you use in longer duration on the grid.
Okay, so what about using a home EV for some energy storage for evening? Do you think it's a viable business model, or this is the?
Well, again, it's a matter of warranty issues from the EV companies, right? I mean, you're using your battery for as a storage device, then where did the warranties come from? So I think it's a more a business proposition, not necessarily the technical issue.
So that is basically people talk about the V2G or V2X. Is that right?
Yeah. V2G is again most of the, let's say if you look at V2G, would your car company allow you to supply energy to the grid? And if so, does your warranty covers? So I think it's a lot of these things are business practices that I think will be resolved as a matter of time.
Okay, so to which degree can lithium from battery be recycled? Could a long-term projection be that some point lithium mining would no longer be required, just like a lead-acid battery?
Well, I mean, I think the question is how much the primary lithium supply is going to be. Right now, the competition is between primary lithium and recycled material, right? And the primary lithium is just a commodity. And 3 years ago, when lithium carbonate was $80,000 a ton, recycling made really valuable sense. So I think it runs with the commodity markets. But let's say as you look out, maybe 10 years out, you have significant volumes to sustain a viable businesses. I think there's no reason to think why we would not have a full loop to recycle all the materials, at least the critical materials.
Okay, so do recycling facility use a large amount of water? And how is this managed within the goal of a circular economy? Because the water is another precious commodity.
Yeah, I don't know how much water they use, but it's probably significant. And how much of it is, it is a closed loop process, I don't know. So.
Yeah, the other one is not within the scope of this webinar, but I will basically addressed it. Can you share the PV recycling typical commercial cost versus the EV cost?
Well, I think these are two different things. I mean, you're comparing PV is, photovoltaics based on silicon cells versus EV, which is a lithium batteries. I mean, those are not direct comparison. And also they have totally different cycle lives. I mean, if you look at a typical PV plant, the operating life of a typical PV plant is about 25 years. And silicon is it doesn't have any environmental issues and rarely recycled. So the recycling in PV business is all about aluminum frames, silver, and other things. That what comes up to be more important, not the silicon itself.
Okay, and this is on everybody's mind when people own a EV electric vehicle. That is the battery life. So is any technology that could EV battery be reconditioned to extend the EV battery useful life?
Well, I think this goes back to some of the questions about the battery management systems, which are proprietary. A car company owns that, right? And unless you have a good data sets on knowing what the battery has gone through during its lifetime, which also means you have access to a full life cycle data, it's hard to see how we can recondition. Reconditioning could be just knowing how much capacity do you have beyond nameplate, right? I think that goes back to knowing the data, use data, and would the auto companies provide you that?
And then the other one is to basically monitor the distribution of the battery. And in Europe, they are talking about digital passport.
Right.
Do you think that the digital passport technology will narrow the gap that you have mentioned in your presentation?
I mean, it'll help. Okay, it'll help as we look at the recycling.
Okay. Any other question from the audience? Well, if not,
Rajan, you're on mute.
yeah. So you can hear me now?
Yeah.
Okay, so that this basically conclude our webinar. And then, Carol, do you want to make a closing remark?
Thank you so much, Weijian and Babu. This was really an excellent, informative webinar that was really very appropriate for closing this first series on our circular economy. So we invite everyone who has attended and registered for the seminar series to look for the second series to be announced soon. And also in your survey to please suggest other topics that you would like us to address in our next series. So thank you so much.
Okay, thank you very much. And everybody, nice rest of the day.
Yeah, thank you.